Alright, let's get started. So I changed the title of the talk to be high-performance computing means machine learning and vice versa. It was supposed to be about GPU metaprogramming, but I thought it would be better suited for this workshop to talk more about some sort of synergy between machine learning and high-performance computing. So let's get started. So I'm going to talk about high-performance computing aware machine learning and what can we bring to the table and why it has been very useful to us. Then I'm going to move another diversion on the actual GPU metaprogramming and why it's important. And then we'll get back to trying to convince you guys to kind of like merge some of your work with the high-performance computing community and try to see if it's possible to have some machine learning awareness in high-performance computing. So help having some machine learning tools and techniques to help high-performance computing. So let's get started with the HPC-aware machine learning. So let me present you like what I'm working on. So I'm interested in the problem of visual object recognition. Why, you may wonder, you probably all know that it's a complicated problem, but a lot of people, including my mom, think it's actually easy and it has nothing to do with intelligence. And actually many people in the field thought that would be actually pretty easy, but they will solve it in the summer. That's actually nice to remember that actually we were like kind of wrong about this problem. So what do we mean about visual object recognition? So that's the fit that humans have, which is really, really fast, organize many objects, very highly accurate, effortless. You don't have to think about it, you just see. It's not like solving a very complicated mathematical problem, you just open your eyes and you see. It's critical to survival, so for mate selection, for danger avoidance, for food seeking, it's very, very important. And computationally, what makes the problem really, really hard is the fact that you have to tolerate a lot of image variation, scale, position, illumination, occlusion. So why is it hard from a computational point of view? Well, first of all, the world is three-dimensional, but once the image hits your retina, it's actually a two-dimensional projection. So you're in front of a hill pose and actually hill condition problem. Once the image hits the retina, you're activating in the order of 1 million retinal ganglion cells, so the dimensionality of the problem is extremely high. And again, you have to deal with considerable image variation. And the fact that it's so easy for you is because basically there is a very large fraction of your brain, a very large fraction of one of the most complex things on Earth that is dedicated to, or at least driven by visual processing. So that's why it's so effortless. Evolutionary, we are so visual, and the reason why we don't like to think about it is because a lot of the brain hardware has been dedicated to this. Actually, a lot of people think that you have learned to see. Like there is some parts are hard-coded, but all of them have been actually learned throughout the development. And you too, you were actually putting the square in the circle. So you actually learn to see even though you don't, probably don't remember. Some background, so in our labs we are interested in reverse and forward engineering the brain. We think it's a really interesting idea to do that in the same lab. So it's just some people studying biology and other people doing the engineering. There might be some synergy that could happen if like the same groups of people do both. So we're interested in reverse engineering the natural system because that's kind of an instantiation of a working system. So we want to study how the natural system works and try to formulate computational hypotheses, implement them in artificial systems, real large-scale, not toy problems, large-scale computational systems and try to see if they work. And what we hope is that there will be some really nice synergistic interaction between the two. Thanks. So what do we see when we reverse engineer the brain? What we see is that once the image hits the retina, then it goes to like a part of the not of the brain, but like part of the brain is called the RGN, which is not cortical yet, but then it hits the primary visual area, which is V1, then V2, V4, 90, and once you are in that domain, the problem is basically solved. And the way people think about it is they're thinking about this transformation as being this kind of canonical module of this canonical circuit that's being applied again and again. Exactly the same function, the only thing that changes is the input and the output of that function. And we are really hoping that's the case because engineering-wise, that would be much easier to understand the brain that way. People think that cortex is cortex, cortex then changes the input that flows into the circuitry. You're probably more interested in this computational fact about reverse engineering the brain. Some conservative estimates about the computational capability of the brain is around 20 petaflops. That's a lot of compute power in your brain. And if you think that, I don't know, half of it is dedicated to vision, then it's like 10 petaflops to be able to see the way we see. So that's a very, very large number. So if you want to solve visual tasks, you probably need to think about big data, big learning, and big machines. So when we started to work on forward engineering this part of the context, we thought it was all about learning. And all of this computational power was to actually extract statistical regularities from the spatial temporal data that is hitting your retina. And we really thought it was all about this kind of like semi-supervised learning. How do you learn the synaptic way? We were sure that would be the case. That's why we kind of moved to like build GPU machines and whatever. But what we saw is that it actually doesn't matter that much. What matters more at this point is the parameters of the circuitry. Like if you have like 2 or 3 layers in a model, it doesn't really matter if you learn or not, at least for now. It doesn't mean that we have the right recipe, maybe we didn't code it well. What matters the most is all of these red parameters, especially the ones that have nothing to do with learning, like the number of filters, the number of units, the number of layers, the kind of non-linearities in the network. But this, for some reason, matter much more than doing any learning. And that's what we saw very early on, and that's why we had to move to kind of like change our schedule and work more on the hyperparameters and less on the learning. So usually, how are these things done? Like, how does it work? Usually, the usual formula is you take one grad student, you will play with a model that is usually limited by runtime and the library that is currently available in the lab. You test it and you try to get some nice results on some external benchmark. And hopefully you publish that on a nice paper and you get a PhD. And the problem with this is that you're basically limited a lot by the size of the model. And since there are a lot of parameters, you want to be able to tweak them, it takes a lot of time, it's kind of like complicated. So a lot of people call that actually graduate student descent. This idea of having this model and actually a graduate student will tweak it, try to see if it works on one benchmark and then another one. And a friend of mine was saying that, you know, what would be better than this? And he mentioned maybe take 2 graduate students together and do some sort of conjugate graduate student descent together. It works, and if you have multiple people kind of tweaking the parameters, that would kind of probably be faster. But that would be nice if we could kind of automate that and have machines do this work instead of us. So we're trying to do this. So let's do it a little bit differently. We take that same grad student and we're going to try tons and thousands of big models, try to just like kitchen sink it. Mostly because when I started this project, I didn't know anything about literature, I didn't know what was right, what was wrong. People are very opinionated about what works and what doesn't work. I just wanted to learn for myself, so it was just easier to just throw kitchen sink at the problem. Hopefully you'll get some papers out and keep the idea. So I'm a really big fan of Linus Pauling, Global Nobel Prize winner. And if you ask him, so some of his students and some of the people working with him were asking, how do you get so many good ideas? Why are you so good at this scientific game? And he was saying, if you want to have good ideas, the number one thing is just have tons of them and learn how to be quick at skimming out the good ones and throwing away the bad ones. The problem is I'm not in this Pauling, so I'm really bad at throwing away the bad ones. So I'm relying on computers to throw away the bad ones. And that's called brute force. And I mean, you can call it something else. We actually found a really nice term in biology for this. But that's really brute force. What's really nice about brute force and this kitchen sink approach, let's try everything and see what works and then study them, is that if it doesn't work, that's because you just didn't use enough. You just need to put more machines on the problem. And if you put more brute force, at some point, something hopefully will come out. I think a better name, we call it high-throughput screening, this brute force approach that they have in biology. So here we try to build like a very large family of 5 models. 52 parameters, if you want to the it's 10 to the 25 possible unique combinations. We try to be very inclusive, have some of the secret sauce of some groups, the product space of all of these potential combinations. So try to see what we right and try to understand how this kind of model works. The problem is here, like so many parameters, really big models on big data. It's problematic. There's thousands of big models, and we still wanted at the time to have large amounts of unsupervised learning of the brain in the normal brain. At the time, there was no off-the-shelf solution to
of engineering. Less science, actually close to no science. So the kind of result I'll show you, there is absolutely no science. And a lot of engineering, so taking on the hardware, software, demonstration, try to do some science at the end. And to do this, we try to capitalize on other markets that are investing a lot on like building really computationally heavy machines. And we try to capitalize on two markets, Web 2.0, cloud computing, Amazon, Google, and gaming hardware. So you have this like massive amount of R&D that is like spent on trying to make this graphics card and these game consoles go extremely fast, just to be able to play Crysis like really, really quickly and have this really nice environment to play. So if we can capitalize on that and take this computational power and put it on my kitchen sink approach, that would be nice, because then I will be able to do it very quickly. Graphics cards are also kind of nice because I'm interested in vision, and graphics cards produce visual world. I'm interested in inverting that process, so they kind of fit very well in this thing. So we built a lot of hardware that's kind of fun. This made it to Slashdot. That was kind of interesting. So we've been playing with the GPU since 2006. At the time where it was kind of complicated, you had to use like a graphics creator. And then we moved to version 3, and then we moved back to GPUs. In terms of speed, we were able with the techniques I'm going to mention later on to be quite fast. So here I'm doing kind of a very unfair comparison. I'm comparing against like MATLAB if you code it, if you try to implement this model with MATLAB, still using like the FFTs of MATLAB, the convolution of MATLAB, what kind of performance you'll get in terms of gigaflops. And at the time where we did this plot, it was like around like 0.3 per core, so one single core, very, very slow. If you do the job of like coding it for the CPU really, really well, you can approach 10 gigaflops. But as soon as you get into the GPU or PlayStation 3, you get like orders of magnitude faster. You don't do the same type of science with it. Actually, you don't do much science at all. And 1,000 times speed up is game changing. So you could be like a nice grad student and ask very stupid questions because you get your answer right away. So you can afford actually to not think. And me as a computer scientist, I like that. It's kind of the computer doing my work. And if I get some good results, they actually tend to be less biased because you tried so many potential models. So high-throughput screening. So we did brute force search. So since it's going so fast, we can just throw away large features at the problem. And what we do is that we take tons of different models, different ideas, and different thoughts, and test them on some small task of object recognition, for example. And here you can see the count of this program here. So the count of the models we screened, we just screened 2,500 models on PlayStation 3 at the time, it was a week or two. And you see the performance is kind of not really that good. If you have a stupid baseline, most of the models are actually below the stupid baseline. If you zoom in, what you see is that a few models, for some reason, just popped out. And it's a really good one. So the brute force approach is just to take these models and try to see if you can analyze them. So here, it's brute force search on this space, so it's really kind of overfitting this but I'm still getting really good performance. So how about I take these 5 models that are overfitting on the kind of like screen good performance on the we tested on other labs. Now we play a lot with synthetic images because we can control we render images onto various backgrounds to try to see if they really expose the difficulty of the problem. The problem is all about the image variation. They are not natural, they don't look natural. You don't see clouds floating in the sky usually in your life, but what you see so when people compare against like a neural model, if we do this against the state-of-the-art at the time in computer vision, this were produced to match their performance in Cortex 1.1. What you can see is that some of them are actually getting better than this D1-like baseline, D1-like based on Gabor. And all of the other ones, like maybe against this Max one, all of the top 5 that were not screened on that particular task are actually getting better than this state-of-the-art. But again, not pretty natural. It's controlled, but still it's kind of like a very small test set. So we tested on faces. Here it's very interesting. On faces, most of these features are actually pretty bad. People use other type of features, other type of models for faces. But still, these top 5 models, for some reason, kind of generalized to faces. Kind of an interesting thing. Again, synthetic faces, far away from natural images. You may think it's actually not really that interesting. But we'll follow up on that. We compared against humans. We are in neuroscience labs, so we can compare against humans. Things like compared to the baseline, we are halfway through. We have still a long shot to actually reach human performance. So now we have good models. We can start analyzing them. We have so many of them. We can analyze them and try to see what works, what doesn't work. What we saw very briefly is that the dimensionality matters a lot. If you have a lot of filters, like
we are halfway through. We have still a long shot to actually reach human performance. So now we have good models, we can start analyzing them. We have so many of them, we can analyze them and try to see what works, what doesn't work. What we saw very briefly is that dimensionality matters a lot. If you have a lot of filters, like really big gatherers and tons of them, it works much better than when you have a small model. So that's nice because you can run that with GPU. Learning is really, really difficult. What we saw early on is that if you disable the learning, you're as good as if you learn with it. So sometimes some models will get better, some won't get better, but overall, if you play around with a lot of the hyperparameters, learning doesn't seem to work. So the learning algorithm we implemented didn't seem to work. The non-linearities are very, very important, most particularly the normalization. Normalization was kind of missed by other models, and now has been embraced by other people working on similar models, and now they boosted their performance drastically using this normalization, which was very inspired by lateral inhibition, kind of competition between neurons. So non-linearities are very, very important, and thanks to this approach, we're able to show that. So what are they not good for? Actually, they are really good for objects and faces. They are really not good for background. So if you put them on the data set that most clear rely on background, like Caltech 101 or Pascal POC, that even if you remove the object, you're still really good at recognizing the object. These models are not that good because they are for object recognition, not background recognition. So they are kind of bad for background. So that's it for the first part, HPC-aware machine learning. Oh, wait, sorry, one more thing. So some people say that they don't like the fact we use synthetic images. So they are wondering if we can actually build real-world, natural applications with this approach. So we wanted to test the generality and scalability of the approach. So we took some really real-world problem. We took Facebook, which is like massive amount of data, tons of faces. People actually collected, tag, and annotate these faces for us. And so we collaborated with Axton and Tanzika on hardware for this, and we try to see if it's possible to apply this very simple random approach, brute force, to this large-scale problem. Why is it relevant? Well, if you can build models that kind of capture faces for social networks, you can maybe infer some relationship that was not in the social graph, and of course you can develop like targeted advertisement. It seems like social networking is really interesting in this problem. Again, the same approach, brute force. Alright, screening, the way you want to take it. We did the exact same approach. We took like a screening test that was like face recognition. That was not at all part of Facebook. And we disabled the unsupervised learning. We actually removed the unsupervised learning because it was making everything slow and the models were really bad. Same approach. We tested on a legal face in the wild, which is like a common natural benchmark in face recognition literature, and we're able to get much better performance than the current state of the art. But that's it was going to be kind of good at this, even if it's more our data set. It's still not Facebook. So then we took Facebook, we took like a typical social network size of 100 friends. The classification is taking 100 people and being able to identify it. And we were able to get 86% accuracy. What does this mean? Not much. What we can do, however, is take the best recognition technology out there, which is Face.com, they advertise as being the best technology around, and compare against them. So that's what we did. And with this stupid hardware accelerated brute force random, again, no unsupervised learning, training on GPUs, for just a few days we were able to outperform Face.com, which is highly specialized just for faces. Again, this approach can be mapped.
Matter, it changed for a Mac is really happy about it, much faster, much better. The hardware is really important. So, just the hardware accelerated learning that we're talking about. Okay, let's talk about how we got this performance out of the metaprogramming part. So the brain is massive power, 20 petabytes. Big models are really that's kind of competing things. You want to have something fast to run them really quickly, of course, let's be able to explore them. But you also want them to be flexible, right? You want to be able to play around with the parameters. Different models, they are very, very different. Some actually, if you look very closely and you try to like most of the approaches, they are mostly relying on 3D filter bank. So if you are trying to accelerate just that specific operation, you need to accelerate most of the data. So our answer to be able to tackle this problem was to use metaprogramming. So what is metaprogramming? What is this idea? Well, metaprogramming is like this idea of having programs that work right programs. So you leave the ground programming to the computer. You can use in the most successful signal processing libraries and linear algebra libraries like Atlas, the automatically tuned linear algebra subroutines and FTW. When you use these libraries, they're actually auto-tuned to be a metaprogram to generate the best code for your particular hardware. So how do you do this? Well, when you start programming with GPUs, there are a lot of options. You can have different block size, work size. There are a lot of different techniques to optimize this hardware. For GPUs, multiple, whatever. The idea is to just implement them all as you learn how to program GPUs, and you just let the computer try to find the optimal code. You'll try, again, the same approach, like random kitchen, you'll try a lot of different variants and find the best one. So to do that, we tend to try to see what would be the best tool. So what we use is Python, which is kind of like a little bit weird, right? We're talking about high-performance computing, and we're going to use a cryptic, slow language. Well, Python might be slow, but to generate tons of different codes, it's actually quite fast. And what really matters is the C code that you generate through Python. So what we use is like template metaprogramming, so we just use some Python in some C code to be able to template the C code very easily. You could use C++ templating as well, but it's much faster and much easier to do it with Python because it's high-level language. So you can inject some Python inside your C code to metaprogram your GPU kernel. So we use PyCUDA for this, so that helps us kind of like do the heavy work of like compiling the source code which is in C and loading it onto the GPU, executing the function. So everything is kind of in Python. As soon as it hits the GPU, of course it's in like GPU opcodes and GPU binary code. So only kind of like the driver is in PyCUDA and Python. So our basic GPU metaprogramming system looks like this. So we have a template engine in Python that will kind of get a kernel template that you program. You will generate tons of them and compile it, get some performance metrics, and try to see if you can understand how the hardware works and try to get like better and better performance out. So the kernel template may look like this. If you actually render this kernel, you will start getting this really huge files that actually unroll the loops for you. For example, if you have a 4x4 kernel that is like a template metaprogram, you may end up with a source file completely unroll. You don't let the compiler do any optimization. You are the one controlling the optimization. You may get a 20 kilobyte file. If you do 8x8x4 convolution, another file. And all of that is kind of cached by PyCUDA, so you don't have to regenerate them later on. So the benefit of this approach is that if you do a lot of optimization, if you're used to do a lot of optimization for this hardware, a lot of time it becomes really, really ugly very, very easily, right? You get like all of this optimization, the code is unreadable. With template metaprogramming, you can actually smooth this syntactic ugliness. Because it's in Python, like doing the loop unrolling, it actually looks like a real loop, except it's in Python as in C. And actually, once it gets rendered, it's all like you can do unrolling and jamming. It's kind of, you don't care about the C code, you just care about the Python interface. You could do, of course, you could use the pragma unroll from the compiler, but it just happens that the compiler never really does what you want. And even if like two operations look the same, for example, this operation here and this one, if you use this one, which is exactly the same as this one, you'll get a teraflop, whereas if you like this one, still an VCC, a recent NVCC from 2011, this year you'll get like 30% less. So never trust really the compiler. The compiler technology is really good, but once you are into really high performance computing, you won't do the work. Other stuff we can do, we can have variable length argument lists for C very easily. A lot of different things that we can talk more about the details, but this doesn't really matter here. What's important is that you can have really the freedom to explore a lot in your code. So if you're interested in implementing, I don't know, you read a paper about a nice optimization technique. What's cool is that you can implement it, let it in the code, have just a branch that will just select this variant against the other, and you can explore how the hardware works, how the software works, how the optimization technique works, and just have really nice and compact code. So you can hand-tune and try to understand the hardware if you are into this, or try to get as many insights about the problem or the hardware that way. And since you're operating in high-level language, it's kind of much easier, much faster, you can write stuff very easily. The problem is that once you have so many optimizations, it's kind of hard to keep up with, and you may want to keep them all. So if you cannot decide which optimization to use, it's just better to just put all in there, and again, let some sort of auto-tuning algorithm figure out what's the best combination of all. So metaprogramming enables efficient learning of the GPU architecture. If you are into this, maybe this audience is not that interested in learning about GPUs, but we learn a lot about the architecture through this technique that was not available in the programming guide. And at the end of the day, you can really exploit entirely the GPU and try to get very, very close to the CPU. In terms of results, your exam, this hand tuning, this is never really going to stop. You cannot take your best code right now on the current hardware or current input to translate it to another hardware or optimize for one another. Okay, the summary metaprogramming has this exploration and optimization. People like the kind of hardware. If you want to understand how it's not very well developed. It's really cool because you can get a lot of insights about the hardware. You can declare highly optimized because you're working at a scripting language. It's very easy if you use the right tool. So Python, Calcutta, and so on, it tends to be, not this the appropriate word. It's not that easy. It's just easier. It will help you get drastic speedups. We got like really drastic speedups very easily, and it will facilitate auto-tuning, which is the topic of the next section, which is trying to bring machine learning into high-performance computing. So see all of these different variants of code. If there could be a machine learning algorithm that could find the best code for you instead of doing random search, that would be really nice. You just code them all. You let someone code all of the different primitives of optimization for you, and you let machine learning, really good machine learning algorithm try to find the code for you. That would be nice. So that then you have nothing to do. So that's the topic of this section, which is trying to have intelligent and fast auto-tuning with machine learning. Why do I say fast? Because it could take some time to generate the best code, for example. So if you can have a technique that is like both really, really fast in terms of the code it produces, but also fast, I can get this code very quickly, then we'll be in really good shape. And that's work primarily done with James and David Cox. So if you want to talk more about the technique that we use, you should poke James about that. So really trying to bring machine learning to the high-performance computing community. So in auto-tuning, generally there are two approaches. The first one is the analytical model-based approach. So the pros of that one is that it's very generic. So the idea is to build an analytical model, a mathematical model of the hardware, of the code that you want to optimize, of the input. You try to do a mathematical model, a pure mathematical model. So it's really, really fast doing the inference. You just need to derive the model, and you can get the best code for a particular hardware or a particular instantiation of the input configuration. So it's very, very generic. That's what all the compilers do. They have a model of the hardware, and that's how they get the best code. If you do VC-03, that's the kind of technique that it is. It's very fast. It doesn't have to kind of empirically tune your code. The problem is it's kind of hard to build this analytical model. It's a lot of manual work. Someone has to come up with this analytical model. And finally, you're basically bound by the quality of this abstraction. If you have a lot of degrees of freedom in the hardware, it's going to be extremely hard to build, almost impractical to build mathematical model. And you need a very high quality domain expertise to be able to do it. And as a result, since you're bound by the quality of that model, the model tends to be simpler, and usually your code that is auto-tuned is far from what you could really reach. That's why the compilers don't really do what you want them to do. The second technique is called empirical optimization. Empirical optimization is really, really good because it's just trying a bunch of kernels. That's the approach of doing metaprogramming, right? You try a bunch of variants, you pick up the one that is the best, and you cache it on some sort of data. So it's really, really good because you'll get close to the peak that you will be able to get. And that's what's usually used for these libraries, highly specialized libraries. These libraries really want the best code, so that's the kind of technique. Empirically, try all of the different variants and get the best one. Very easy to build. You don't need to build an analytical model. The problem is usually it's very slow when you want to generate something that was not part of the empirical optimization. So if you have a new input, you optimize for a bunch of inputs, like power of 2 input. If you have a non-power of 2 inputs, then you have to cast it as a power of 2. That's how it's going to run fast. But if this empirical optimization was not tuned for something else, it will be extremely slow. You will have to do all of this empirical tuning again and again every time you have a different input. The problem is that in our application, we have all of these different inputs, different parameters, they constantly change all the time. We don't always do an FFT, which is in 2048, for example. So we need something that has kind of the best of both worlds, being able to be really close to peak, but without having to build a complicated model. And that's where machine learning kicks in, basically. Okay, so is it possible to have the best of both approaches? Is it possible to combine kind of what's really good about the analytical model, the fast inference, like being able to predict what will be the best code for a new input, a new hardware, and also the close to peak performance of empirical tuning? Well, there seems to be one because James found one, and that's something that here I'll call empirically learned model-based optimization. And the pros are basically all the pros of both approaches, and maybe the cons will be that the fact that it's unexplored. And that's why I'm going to talk to you about this, that if the machine learning community could work on this problem, that would be, I think, really good, because there will be this synergistic relationship between both fields. And you could maybe optimize code for high-performance computing design and get this kind of loop that would be a really nice foundation. Auto-tune code close to peak, that could be that's really what you want, right? That's what you want for specialized libraries. We are all into specialized libraries that really focus on SVM, for example. This could be a specialized library for high-performance computing that could be using this approach for auto-tuning itself. So you could bootstrap the entire auto-tuning aspect. That would be kind of interesting. So that's what James tried to do recently, and after really all the night, I was able to pull that through. And so we pushed the paper with boosted regression tree. So we used like a boosted tree to try to be able to predict, and it seems to be working quite well. So again, on the 3D photomatic convolution we saw before, we tried the parameterized code that I mentioned before, and James ran his algorithm. What we saw is that if you do empirical tuning, the slow version, the one that kind of tests all of it, give him a new input, it will take minutes to come up with the best code. This one is on the x-axis. Yeah. It takes minutes to actually generate that best code. And if you take the approach that James developed with the decision trees, it takes less than 0.1 seconds. And if you look at the performance reached by both of these approaches, they are very, very well correlated. So with a fraction of a second, you actually can get the same performance as if you were doing the empirical tuning. That seems to be kind of going in the right direction. And that was kind of a first shot and seems to be working. And again, if you look at this point here, actually, with the GX580, it's 1.1 teraflops of observed performance. That's 80% of what the machine can do. It's almost close. You cannot really get much further. And this approach was able to find it very quickly. So what else could we do with this? So what we can do is try to minimize
teraflop of observed performance. That's 80% of what the machine can do. It's almost close. You cannot really get much further. And this approach was able to find it very quickly. So what else could we do with this? So what we can do is also try to minimize failure. We can try with machine learning to understand the failures of multiple cores, whatever. So why is it important? Well, for exascale supercomputers, when you have like thousands of cores, the likelihood of one failing will be extremely high. So if we can have machine learning approaches try to predict which one will fail under what condition, that will be also very interesting. We can also try to minimize NIPS precision errors. So a lot of times what really limits the performance of a given algorithm is the amount of data that is getting transferred, the memory and communication. So a lot of people resolve to try to do some really nice techniques about NIPS precision. Basically, instead of using double precision, you use half precision, which is much smaller in the memory footprint, so you communicate less bytes. But then you have some sort of errors because numerically, an addition is actually not commutative numerically because you can accumulate errors. So depending on the parallelism and the multi-threading techniques that you're using, you may get different errors.
I think this will help better understand the hardware features and how they interact with each other. These hardware features happen to become extremely difficult to understand, especially their interactions, because now that we have parallel processors, no one really knows what's the best architecture. No one really knows what to do, so they just have tons of different features. That's why it's extremely hard to do the analytical model. because no one is sure how it will work in terms of the architectural details. Before, back in the days in the single core, everyone was kind of agreeing on how it should be architectured, so it was easier to do an analytical model. So here, maybe we can understand better the complex interactions, and maybe help the high-performance computers and the hardware designers to design better architectures that way. Hopefully, we can get this synergistic relationship. And maybe they can sell more, high-performance computing hardware for us, and we can have some profit out of that. So from my point of view, that would be a win-win-win situation. So if you can think a little bit about the problem, maybe you'll find a small nugget that could be interesting, and just try to talk to an high-performance computing guy, and maybe you'll be able to get something interesting going on. So that's it. That was the outline. So again, HPC awareness in machine learning. We all agree that's important. That's probably why we're still here. And my attempt here is to try to bring you to the table with HPC people and try to see if we can come up with something. So I'd like to thank my lab, Nicolas at MIT and his lab, and David Cox at Harvard. The sponsors that have been supporting my research and my teaching, and you for coming. Thank you. Any question? So this has been done in what's called iterative compilation with genetic programming. So it works really well. The issue is if you give a new input in your hardware, it's very slow. So this fast inference problem it's not getting solved there. But that's maybe there is more research to be done in GPs to try to be able to balance out the cost. That's a good point. Thank you. So the input space will be a very discrete interface. So for example, a parameter that could be you do unrolling or you don't, like a bunch of parameters like that, and the output is the time it took to run this particular configuration of options. So how many threads do you use on this particular processor? This kind of, it's actually, when you look at it from when you look at the parameter space, it's highly discontinuous. It's a very hard combinatorial optimization problem. And actually the best performing code are usually at the cliff of the best performance, because that's where you hit the hardware resource limits. So the space is kind of complicated. But just like a bunch of options. I don't know how to describe it in better mathematical terms. Yeah, or power efficiency, yeah. I think it's more. No. The point I should have had is here. If you could optimize for any combination of load. Yeah. Thing with the metaprogramming code, not the machine learning one, but that is not accepted yet. The metaprogramming is the proof of concept that programming is related to a book chapter, and it's supposed to be released as soon as the book is released. But it's a proof concept to have all of the things to make it a real library. To make it a real library, you have to have many more options. because the data layout matters a lot, depending on if you have like a very fast convolutional net or very thin with a lot of features, for example. It's very different. Yep. Yeah, so the issue with this kind of like compute primitives that are like generate enough, is that a lot of time you don't get peak performance because they are too generic. For example, you could say, well, in convolutions, just do an FFT, right? Just do it in the Fourier domain. And the fact is that this convolution, here is a filter bank. There is another dimension of the data that FFT is not aware of. So to get maximum performance, this library needs to know about the fact that it's a filter bank. So here you're probably talking about trust or like QGTP, this like parallel primitives that they are developing. A lot of times you cannot get peak performance on this kind of stencil operations for various reasons. So if you make the library very generic in terms of stencils, maybe you can get them to work with this compute primitives. But again, this is kind of side projects for us. So these are all very interesting questions. If we had more time, or if you guys want to collaborate, we'll be happy to talk more about.